Good afternoon, everyone. I want to welcome you all to our 13th Hans Liebe lecture. I've listed here our previous Hans Liebe Fellows. And true to form, we have another fellow this year who's going to be giving us a lecture on his work in the area of microwave and optical spectroscopy as applied to radio science, Earth remote sensing, radio astronomy, and telecommunications. The USNC-URSI, with the generous support of the Liebe family, has established this lectureship on these topics. It provides travel support and an honorarium for a distinguished member of the radio science community to deliver a lecture on the professional topic of their interest at each of the radio science meetings. This fellowship commemorates Hans Liebe and the contributions he's made to radio science during his career time. And it allows us to honor a fellow member of the radio science community in allowing them to speak about their contributions as well. As we all know, Hans produced the atmospheric millimeter propagation model, which is used by a lot of people today in the area of radio astronomy, Earth remote sensing, and various other related fields, telecommunications. It's withstood the test of time. Our 13th Hans Liebe Fellow is Dr. Juan Pardo from the Consejo Superior de Investigaciones Científicas, the Spanish National Research Council. He is a research scientist at the Research Council, obtained his PhD at Pierre et Marie Curie University in 1996 at the Paris Observatory. He later worked in the US at NASA, Columbia University, and Caltech. During his 30-year career, he has applied molecular spectroscopy to both astronomy and to terrestrial remote sensing research. His millimeter and submillimeter wave atmospheric radiator transfer codes, based on state-of-the-art experiments, are used by observatories such as ALMA in Chile and Institut de Radioastronomie Millimétrique, IRAM, in France and Spain. In addition, Dr. Pardo has served as counselor for culture for 16 years in his hometown of Fuenterrabía, Spain. There's a population of 1,700. And he has organized over 700 performing arts events, including several operas. Dr. Pardo's talk is it all started with Hans Liebe's MPM, 30 years measuring the atmospheric millimeter wave, submillimeter wave spectrum from dry and high astronomical sites. Without further ado, Dr. Pardo. Bring up your lecture.
All right, thank you very much, Alvin. So I would like to start by thanking the U.S. National Committee for this fellowship, this distinction. It came as a total surprise for me. I didn't know about the existence of this lecture series, and when I received the phone call by Alvin, it was, as I said, a total surprise. At the beginning, I thought that I didn't deserve it, but it is true that for 30 years, I've been working inspired by the work of Professor Liebe, as you will see in my talk. So I started my career in Jebes Observatory in Spain. It is an observatory located at 70 kilometers from Madrid, very close to Madrid. And I started there using this telescope here inside this dome. It's a 14-meter telescope operating at 7 millimeters. And I was in charge of, by the way, this is a picture of me as a young graduate from Madrid University in 1992. So I started by taking over the silicon monoxide monitoring with this telescope. So it turns out that this molecule has major emission of 7 millimeters from evolved stars, pulsating stars of Myra type. They have periods of around 300, 400 days. And actually, by following the major emission, you can follow the pulsations of these stars. And well, we did a pretty good investigation here to demonstrate that actually the measure is pumped by the infrared emission from those stars. This observatory is part of the Geographical Institute of Spain, and this institution is also part of the Iran Consortium, which is a German, French, and Spanish consortium that operates two observatories. One of them in Granada, Spain, Pico Veleta, the famous 30-meter antenna. And we have this wonderful picture of the Alhambra Palace with the 12,000 feet tall Sierra Nevada, where the telescope is located, this one, 30-meter. And the other observatory is the Plateau de Bure interferometer. Now it has, I think, 10 antennas. At the time, in the mid-90s, there was only 3 antennas. And this is located in the French Alps in France. So the direction of the observatory, of Jebus Observatory, decided that the student should work on atmospheric models that are necessary for the millimeter and submillimeter observatories. So that's the reason I landed in Paris in 1994 at Meudon Observatory, and then my research group moved to the historical Cassini Observatory in the center of Paris, which is this beautiful 17th century building, oriented north-south along the Paris Meridian, which is actually the line that crosses that way, like this. And it goes actually through the middle of the Louvre Museum. So this is a slide that I have for students to explain why we have molecular rotational spectroscopy. So if we have molecules with distribution of charge, we have dipolar electrical moment, and this dipolar moment interacts with the electromagnetic radiation, and the electric field exerts a torque. So we have energy levels and transitions. So we need molecules with an electrical dipole moment. But it turns out that in the atmosphere, we have molecular oxygen, which is a totally symmetric molecule with no electrical dipole moment. But this molecule, the fundamental state is the triplet oxygen with 2 parallel electron spins. So this molecule has a permanent dipole, magnetic dipole moment. So it interacts with the magnetic part of the electromagnetic wave. So for oxygen, we have what is called magnetic dipolar transitions. So the difference with the electric dipolar transitions is that the transition probability is 3 orders or 4 orders the magnitude lower. So they're very, very weak. But in the atmosphere, oxygen, of course, is a very abundant molecule. That's why the lines of oxygen and water vapor are similar in intensity. The other important molecule in the atmosphere, which is molecular nitrogen, is totally symmetric, so there is no rotational spectrum. So in millimeter and submillimeter astronomy, we work in a very difficult place of the electromagnetic spectrum. So, and I have a movie that I did some 20 years ago, just to show you the transmission of the atmosphere at those frequencies. So you have the resolution is not very good, but you have frequency and transmission. As you can see, Above 300 gigahertz, which is about 1 millimeter, so transition is basically zero, so the atmosphere is totally opaque. But if we go to high and dry mountain sites, we have atmospheric windows that open. So we have an opportunity to observe at those frequencies. So you see, especially two important submillimeter windows that open at around 650 gigahertz and 850 gigahertz. Okay, so I'll stop this, come back to the presentation. So just a few more words about the spectroscopy. So for water vapor, we have, from the spectroscopic point of view, we have two separate species, para water vapor and ortho water vapor, with multiplicities 3 and 1. And this is related to the spin of the nuclear spin of the protons, the two protons, the two hydrogens of this molecule. So you have transitions within the para water and ortho water, but you don't have a spectroscopic connection between the two spectroscopic species. For oxygen, you have to use two quantum numbers because there's one side is the angular momentum of the molecule, then the angular momentum of the two parallel electron spins. And we have transitions, as you see in this figure. Basically, there's a bunch of transitions around 60 gigahertz. This is what we call the spin rotation 60 gigahertz band. We have an isolated line at 119 gigahertz, and then we have like groups of 3 lines at different parts of the spectrum. So in order to build an atmospheric radiative transfer model, there are many different aspects that you have to take into account. Some of them are in this slide. The radiative transfer equation can be very complicated if you want to take into account scattering in 3D, polarization, etc. So this is a general radiative transfer equation to take into account everything. And then, well, as a young student, when I landed in Paris to work on atmospheric models, the first papers that I got in my hands were, of course, Professor Liebe's 3 main papers, model of published in 1985, 1989, and 1993. This is actually the 1993 paper, presented actually not in a journal, but in a conference. So Professor Liebe basically describes the propagation or the radiative transfer by propagating the fields and taking the time average of the Poynting vector. And the main physical quantity that he describes in his model is the refractivity. Okay? So well, the model is very detailed. It was the state of the art at that time, and still today is a reference and is used by many observatories or many different applications in remote sensing, etc. I was fascinated by the description that he made of the Zeeman effect on oxygen lines, because oxygen, because of the permanent magnetic moment, can couple with the magnetic field, this geomagnetic field, and this gives rise to Zeeman splitting that actually splits the lines in subcomponents that are polarized. So in this publication, this is the absorption for these conditions here, related to water vapor and oxygen. Professor Liebe included 44 oxygen lines, most of them around 60 gigahertz, and 34 water vapor lines. But as I said, I was fascinated by the treatment in this 93 paper about the Zeeman splitting. So this is a simulation he did for a particular oxygen line at around 61 gigahertz. So what happens is that the line splits due to the Zeeman effect, but the splitting is very small. It's on scales of megahertz, so it's very, very small. And each component has a polarization. It can be circularly polarized, left or right, or linearly polarized. I wanted to, the first thing as a young student, as a young PhD student with a lot of creativity, I wanted to actually check this effect. But as Professor Liebe says in the paper, the Zeeman splitting operates above 30 gigahertz. Because of the splitting, and the lines, of course, lower in the atmosphere become too large, and also the rate of collisions destroys the polarization. So you cannot see the Zeeman splitting at the ground. So you need to detect the signal from the mesosphere. What is the problem? The problem is that if you take an oxygen line, the signal from the mesosphere will be absorbed by the signal in the troposphere if you observe from the ground. So it's impossible to observe the Zeeman splitting. So I had the idea of using an isotopic line of oxygen to actually validate this effect. So I choose the 16.0/18.0 line with the frequency is 234 gigahertz. And luckily, at the Plateau de Bure observatory, they had a telescope, small telescope, operating next to the interferometer. The name was Petite Opération Millimétrique. It translates into small millimetric operation. It was a 2.5 meter antenna with a receiver at that frequency. So this is, in this picture, here you have the direction of the local magnetic field in the mesosphere in the location of Plateau de Bure. And I imagine observing in this direction to actually detect what is called the sigma components of the sigma components of the Zeeman splitted lines, which are circularly polarized in the direction perpendicular to the magnetic field, and in this direction to detect the pi components, which are linearly polarized in the direction of the magnetic field. And, well, as you can see the scheme here. So this is the splitting of the two energy levels in sub-levels with Zeeman splitting. Sigma components are these four, and pi components are these. These are circularly polarized, and these are linearly polarized. And these are the results of the observations. You can see that we were able, in the first observation, to actually observe the four sigma components, circularly polarized, and then by moving the telescope to the other direction, we observed the pi components. So it was the first contribution that I did to Professor Liebe work, actually from the ground. So something that he said that couldn't be done from the ground, we imagined an experiment to actually do it. So we did a very nice publication that gave me some reputation among my French colleagues, helped me a lot in my PhD. And as a curiosity, I have to say that during those observations, there was a big, it broke up a big transportation strike in France. That, you know, those kind of strikes are like a tradition there. And so I was supposed to stay for 1 week at the observatory, but I had to stay for 1 month, and I had nowhere to go. Everything was shut down, no trains, no buses, nothing. So I had to survive, and finally I decided to build an igloo to survive for the rest of the month at the observatory. But luckily, building igloos is also an old tradition, a long tradition of the Spanish people. Okay, another aspect that is raised in Liebe's work is what is called the collision-induced absorption. So it happens that we have in the atmospheric spectrum, we have lines, but if you build a model to predict the atmospheric transmission, then using only lines, you will have some transmission like that, but the real transmission is much lower. Especially in the submillimeter windows, you get 20% less transmission. So this is an excess of absorption. And actually, the explanation for that is collision-induced absorption involving collisions of oxygen-oxygen, nitrogen-nitrogen, nitrogen-oxygen, and two main molecules with water vapor. So what happens is that you can consider this system as a large molecule, and instead of having a line spectrum, you have a kind of continuum-like absorption, because, of course, you have many different impact parameters. You have to study the problem statistically as a function of the impact parameter, directions of collision, etc. But, as I said, it is very important to characterize this collision-induced absorption in order to have a precise model for our observatories. So I came to the United States after my PhD that I completed in '96, and I got a postdoc first in New York, and then I moved to Caltech. I was collaborating with a group of Professor Tom Phillips and Gene Serabin. They were running the pioneering submillimeter telescope, the first submillimeter telescope in the world, was the CSO, Caltech Submillimeter Observatory. And we had an experiment to actually do accurate measurements of the atmospheric opacity from 200 to 1600 gigahertz. So we'll see the results. So it's a picture of me in '96, just when I completed my PhD and I came to the United States on the top of Mauna Kea with the CSO behind me. So the experiment was a Fourier transform spectrometer. We had a moving arm with 50 centimeters length. The detector was a helium-3 cooled bolometer. And at the entrance of the bolometer, we had 7 different filters to actually match different atmospheric windows. So we took advantage of the fact that at the top of Mauna Kea, the conditions are quite stable year-round. So temperature at the ground is around 270 Kelvin, and the pressure is 620, and there are very, very little variations. So the dry part of the spectrum remains more or less constant, and the variations are related to water vapor. So these are an interferogram with our experiment. And after your Fourier transform, you get these 3 spectral densities for hot load at ambient temperature, cold load at the temperature of liquid nitrogen, and sky. By combining the 3, we got this beautiful spectra. As you can see, all the water lines, oxygen, but we were even able to detect the most important ozone lines. We did the first detection of a super terahertz window, atmospheric window beyond 1 terahertz, because we had a night in April 1st, 1998, with less than 200 microns of water. By combining these 2 spectra, we were able to actually remove the lines and get the excess of absorption, which is related to the collision-induced absorption, as I said, for both observing runs. As I said, the dry part is the same because the conditions don't change too much, the pressure and temperature. And so we were able to separate on one hand, dry continuum or dry collision-induced absorption, compare it to models, and the wet collision-induced absorption and compare it to different models. After these first results, we acquired another filter to go even at higher frequencies. So we were able to detect 2 extra atmospheric windows going up to 1.6 terahertz in frequency, and we also were able to extract the collision-induced absorption at those windows that this absorption doesn't follow the new square behavior, because at some point in the mid-infrared, of course, it should reach a maximum. It cannot increase forever. So this is the updated model compared with real measurements obtained in Mauna Kea with relatively wet atmospheres, almost 6 millimeters, and here with very dry atmospheres. So you have here the histograms in different colors are real data, and the solid lines correspond to the different opacity contributions. So we did several publications that got a lot of citations afterwards. And we published also in 2001 our own model, in our own radiative transfer model. And in that paper, we had a whole section devoted to compare our parametrization to Liebe's parametrization, because Liebe's parametrization is more like engineering-like, and we were using the definition that is closer to quantum mechanics, using the transition probabilities and so on. So, as I said, we were comparing both, and we were, if we take the lines that appear in Liebe 83, we were doing exactly the same thing, but of course, with the new experiments, we were extending the model, incorporating new molecules, refining the continuum, the collision-induced absorption, etc. We did also in Mauna Kea, in the beginning of this century, the pioneering measurements of phase correction by using water vapor radiometers at 183 gigahertz. We had a whole section this morning in Commission J devoted to that. I would like to show you some results. So basically what happens is that in the absorption coefficient, like that, you have the line shape that actually is a complex function. The imaginary part is related to absorption, and the complex part is related to time delay or phase. But there is a mathematical relationship through the line shape. It means that if you have the absorption spectrum, then you can translate it into phase very easily. And that's the principle of the phase corrections using water vapor radiometry, especially at 183 gigahertz. So what happens is that you have an antenna and you have a screen, which is basically water vapor. You have to imagine that this is three-dimensional and evolving in time. And this will be affecting the phase from your source. So you have a pair of antennas that will have an effect on the fringes. So you need to correct it. We demonstrated with a water vapor radiometer, I collaborated with Martina Bittner, as I said, the pioneering experiments about this technique, with a 3-channel water vapor radiometer installed in CSO and JCMT, the 2 submillimeter telescopes on top of Mauna Kea. And we were able to, as you can see here, measure the phase against an astronomical source, Uranus, and predict the phase with the water vapor radiometer. As you can see, that we were following quite well the astronomical phase. This is another plot that I got courtesy of Bojan Nikolic several years later, where we improved the technique. And here you can see that the phase could be reduced in that particular experiment from 207 phase or path length from 270 microns to 75 microns. So our radiative transfer model, after all these experiments, we got a contract with ESO to actually deliver this radiative transfer model for ALMA. So I was working during 2007 to 2011 doing professional programming to deliver the code to them. But I still wanted to recheck the collision-induced absorption and especially try to get all the details about all these tiny lines that appear in the spectrum related to ozone, isotopic species, variationally excited species, and other molecules that are present in the atmosphere. We didn't have enough sensitivity and resolution with our Mauna Kea experiment to do that. So I was trying to find a collaboration for that for several years. We even extracted calibration data from ALMA when it started operations, but they were not very useful. There were a lot of artifacts, and especially the data concentrate on frequencies of astronomical interest. So it was impossible to get data at all different frequencies. So then I went to a meeting at EUMETSAT in December 2018, and I met Carlos de Broik from ESO, and he showed me this plot here, which was actually an atmospheric spectrum taken by the APEX telescope, which is the Atacama Pathfinder experiment. It's a small telescope very close to ALMA. And they had state-of-the-art heterodyne receivers, optics, I mean, everything very stable. And as you can see here, I was astonished when I saw this for the first time. We have, the data is the black curve. We had all these ozone lines. There's a cluster of ozone lines around 655 gigahertz. And in comparison, this is what we got in our Mauna Kea experiment for the same frequency in terms of atmospheric transmission. So we didn't resolve those lines at all. But here we were resolving very nicely all the lines. Red is the first model that I did. And I said, hey, well, we should start a collaboration, try to find money to set up an experiment. And well, we started to work. As I said, APEX is only two kilometers away from the center of ALMA. So perfect instrument for checking the particular atmospheric model needed for that important astronomical facility. So this is me in 2022 during some of the measurements that we did with the APEX telescope. And basically here you have our model, the opacity contributions, water vapor, oxygen, minor gases of the atmosphere, the collision-induced absorption. This is the 183 gigahertz. This is the frequencies of the water vapor radiometer that is installed at the telescope. And these are the bands covered by the 5 heterodyne receivers available with APEX. And look at the results. This is amazing. So in dark blue, you have individual scans. In black, the addition of all these scans, and in red, the fitting with the model. So you see that now, well, of course, we had a kilohertz resolution, so we're resolving all the lines. We still have some instrumental effects, some ripples, but they are in a frequency scale very, very small, so much smaller than the typical width of the atmospheric lines. So they are not too disturbing. The main problem that we had is that in order to cover a whole atmospheric window, in this case, the atmospheric window going from 557 water line to 752 water line. So in order to cover this, we, with the heterodyne receivers, we have instantaneous band of only 8 gigahertz. So we have to tune the telescope, take a measurement, move to the next frequency, etc. So the whole process takes about half an hour. And if the atmosphere is unstable during this half an hour, so you can have jumps. We didn't have that problem with the FT experiment in Hawaii because the whole thing took only 5 minutes. So we got like an instantaneous view of the whole spectrum. And also, we were able to cover hundreds of gigahertz, okay? So this is the case of a not very good observing session, but Here, August 27, 2022, we did a sky dip of 3 different air masses, 1.0, 1.5, 2.0, very, very stable atmosphere, and look at the results. It's amazing. I mean, black is the data, and red is the model. And you see the residuals down here. And here, all the identifications. Of course, water lines, but we have water isotopes, oxygen isotopes, N2O, etc. So, as I said, all the fine details. I have zooms here to particular frequencies. For example, in here you have HDO, and on top of the HDO line, which is very wide because water is low in the atmosphere. So HDO will be the wide feature here. And right almost at the same frequency, we have a narrow feature, which is ozone, that actually is narrower because it forms higher in the stratosphere. Here, N2O, which is a molecule, has a distribution also very low, and is much wider. The line is much wider than ozone lines. And you have two peaks that are detected that correspond to vibrationally excited ozone in the new tube mode. Here, a bunch of ozone lines. As I said, all these are real measurements with the model on top. Here, a bunch of ozone lines in the vibrationally excited mode nu2, CO, very narrow because CO has a large abundance in the mesosphere, so that's why the line appears narrower with respect to ozone. And this is crazy here. You see ozone here, and all this structure in the data that we thought there were baseline problems, but in fact, when we superimpose the model, you see that, in fact, all the features are real and are related to all these tiny opacity contributions from these different isotopes, etc. So the data are so good that we can even adjust the vertical profiles. Well, this is another atmospheric window from 380 to 520 gigahertz. This is with another receiver around the 325 gigahertz water line. By the way, this is a line which is twin line with respect to the 183. It has almost the same intensity, width, etc. And here you have the model fit residual with an adapted best ozone profile. And if you use the standard profile, you see the large residuals at the positions of the ozone lines. Here at zoom, where you can see the very good fit here with the adapted ozone profile, and here using the standard profile with the with the larger residuals. Okay. And finally, we were able also to recheck, validate the collision-induced absorption. What we did is to actually use the water vapor radiometer to estimate the amount of water vapor, because this water line, 183 water line, is very well known, and we can get very precise values. And then use the whole spectra taken with the heterodyne receivers to also derive water vapor. So if the model is consistent, then in both ways, you should have all the data aligned in a diagonal, okay? And if you remove, for example, here you remove the water vapor collision-induced absorption, you start to have problems, especially for very wet atmospheres. Here we have removed the dry and wet collision-induced absorption. And here we have removed dry, wet, plus the far wings of water lines beyond 1 terahertz. Okay? So that's the way to validate that the description that we obtained for the collision-induced absorption from our Mauna Kea experiment is still valid. So some conclusions of this last part of the work. I have to say that we have a paper that is waiting for me to come back to Spain to be sent to Astronomy and Astrophysics to present all these results. We had 2 more that appeared in previous years. And just to end my talk, this is the situation of our knowledge of the atmospheric spectrum in the millimeter and submillimeter range at the time of Professor Liebe, 1993, and this is where we are now, after all these years. So as I said, I consider myself a continuator of his work, and it has been a very great honor to have the opportunity to give this 13th Liebe lecture. I said at the beginning that Liebe 1993 was not a journal paper, it was a conference paper, and actually the conference took place in this place, Palma de Mallorca, Spain, which is a beautiful city in the also beautiful Balearic Islands, that as well as Granada, that I showed you at the beginning. I invite you, if you don't know, to visit. And I will end here with my deepest respect and recognition to Professor Hans Liebe and his work. Thank you very much.
Thank you very much, Dr. Pardo. This is a really fascinating discussion of work that's led to great improvements in modeling. And we have a few minutes for questions. Anyone?
Yes.
Several decades ago, it was postulated that the water continuum in the roll of terraforms might be due to a very strong line way up in the terraform range. But that's no longer possible. I understand what you're saying is due to molecular condition. 3 decades ago, the water continuum was postulated to be very strong line up in the terraform range.
So if you want the papers,
Yeah, in one of the papers of Professor Liebe, he describes the water vapor collision-induced absorption by including fake line beyond 1 terahertz. That's because in his models, he only includes line up to 1 terahertz. There are many lines above 1 terahertz, and as the lines are very wide, the far wings go into the gigahertz domain, right? So in our model, actually, we include all lines up to 10 terahertz. So, first of all, we take into account all the far wings. And what we are giving in our analysis is really what remains, which is related to this physical process called collision-induced absorption. But this was also discussed by Professor Liebe. He said that, well, this is an artificial way to describe this excess of absorption, okay?
I have a question.
Yes.
Do you think that improvement upon the impact approximation will ultimately be able to shed any better light on the empirical corrections we have to make in the continuum?
Well, the impact approximation is what gives us the Van Vleuten-Weisskopf line profile. From our data, everything is quite consistent. So I don't think there's too much to do now.
Any other questions? Okay, well, if not, there's one more thing, and that is, on behalf of USNC-URSI, we would like to present to you a little token of our appreciation for having delivered our 13th Hans Liebe lecture. This is a little plaque in recognition Dr. Pardo?
Will be on the speaker, so.
Thank you very much, very much.
Absolutely.
Thank you very much.
That concludes our 13th Hans Liebe lecture, and I hope you enjoy the rest of the conference. Thank you.